Sentaos y descubríos, se abre la sesión. Buenos días a todos. Se va a proceder a la solemne investidura de la profesora Bárbara Liskov como doctora honoris causa por la Universidad Politécnica de Madrid. Tiene la palabra la señora secretaria general de la Universidad, la profesora doña María Teresa González Aguado, para leer el acuerdo de su nombramiento. Por favor.
Yo, María Teresa González Aguado, secretaria general de la Universidad Politécnica de Madrid, y en uso de las facultades que me confiere el artículo 68 de los Estatutos de la Universidad Politécnica de Madrid y el nombramiento otorgado por resolución rectoral de 27 de abril de 2016, certifico que en la sesión ordinaria del Consejo de Gobierno de la Universidad Politécnica de Madrid, celebrada previa convocatoria el día 30 de noviembre de 2017, y a propuesta de la Escuela Técnica Superior de Ingenieros Informáticos, una vez oídos los informes pertinentes, y en reconocimiento a su amplia trayectoria docente e investigadora, se acordó por unanimidad nombrar doctora honoris causa por la Universidad Politécnica de Madrid a la profesora Bárbara Liskov. Y para que conste y surta los efectos oportunos donde proceda, expido y firmo la presente certificación en Madrid a 8 de junio de 2018.
Ilustrísimo señor director de la Escuela Técnica Superior de Ingenieros Informáticos, por favor, invite a la madrina y a la doctoranda que va a ser investida doctora honoris causa a acompañarnos en este solemne acto académico. Señoras y señores, levantaos y cubríos. Señoras y señores, sentaos y descubríos. Tiene la palabra la profesora doña Marta Patiño Martínez, madrina de la profesora Liskov, para pronunciar la laudatio de la misma. Por favor.
Buenos días, señor rector magnífico, señores vicerrectores, señora secretaria general, señores directores, presidente de la Conferencia de Decanos y Directores de Ingeniería Informática, miembros de la Conferencia de Directores y Decanos de Ingeniería Informática. Es un honor estar en este Paraninfo en el acto de investidura de una nueva doctora honoris causa por la Universidad Politécnica de Madrid. I will move to English for just to introduce. It is a honor to be in this conference hall Paraninfo in the event of investing a new doctor honoris causa by Universidad Politécnica de Madrid, UPM. From now on, I will continue in Spanish. You have the test in English. Hoy la UPM honra a la profesora Bárbara Liskov con un doctorado honoris causa, no solo por su excelente trayectoria profesional, sino también como mujer investigadora, pionera en una disciplina, la informática, en la que en aquel momento no había mujeres. Incluso hoy somos muy pocas. Para aquellos que no estén familiarizados con este área, quería simplemente decir que la profesora Bárbara Liskov es profesora del Instituto Tecnológico de Massachusetts, MIT, en el Departamento de Ingeniería Eléctrica e Informática. Y para hacerse una idea de su relevancia como investigadora, que más adelante resumiré brevemente, recibió el Premio Turing de A.M. en 2008. Fue concedido en 2008, pero lo recibió en 2009. Considerado el Premio Nobel en Informática. La profesora Liskov fue la segunda mujer a la que se le otorgó este premio. Y la tercera galardonada en toda la historia del mismo. Quiero recordar que este doctorado honoris causa se enmarca en la celebración del 40 aniversario de los estudios universitarios de informática en España. Y fue en el curso 1977-1978 cuando se empezó a impartir el título de licenciada en informática en la Universidad del País Vasco, Universidad Politécnica de Cataluña y la Universidad Politécnica de Madrid. Actualmente, 40 años después, 92 centros universitarios imparten el grado de Ingeniería Informática en España. Hoy, acompañándonos en este acto, tenemos el honor de contar con los directores de muchos de estos centros, quienes con su presencia respaldan este reconocimiento a la profesora Liskov. Muchas gracias a todos por estar aquí. Como saben, la profesora Liskov es estadounidense, concretamente californiana, y fue allí donde estudió, se graduó en matemáticas en 1961 en la Universidad de Berkeley, California en Berkeley. Posteriormente pasó a trabajar como programadora en Mitre Corporation, que es una empresa que realiza investigación en sistemas de información ubicada en Boston. Más tarde, pasados un par de años, volvió a la Universidad de Stanford, donde realizó un máster que finalizó en 1965. Continuando sus estudios para realizar la tesis doctoral en inteligencia artificial. La profesora Liskov finalizó su tesis doctoral en agosto de 1968, titulada A Program to Play Chess and Games, bajo la dirección del profesor John McCarthy, siendo una de las primeras mujeres en doctorarse en informática en Estados Unidos, si no la primera. Quiero recordar que el profesor McCarthy recibió el Premio Turing en 1971 y un doctorado honoris causa por la Universidad Politécnica de Madrid hace 27 años, en enero de 1991, en este mismo Paraninfo. La profesora Liskov, al finalizar su doctorado, vuelve a trabajar a Mitre, a Boston. Es en esta etapa cuando la experiencia en el desarrollo de programas le conduce a realizar sus primeras contribuciones en el ámbito de los fundamentos de los lenguajes de programación y el diseño de programas. Concretamente, en Mitre, primero se encarga del diseño del sistema operativo de tiempo compartido Venus, todo un reto para esa época. Este trabajo fue publicado en el Congreso ACN Symposium on Operating System Principles, que hoy en día sigue siendo la conferencia más importante en el ámbito de sistemas. En el sistema operativo Venus, los usuarios se conectaban a una máquina virtual, donde los fallos de una máquina no afectaban al resto de los usuarios, considerándose un predecesor de las máquinas virtuales que hoy en día todos utilizamos. Posteriormente, fue encargada de estudiar la crisis del software. En este contexto es donde realiza sus primeros trabajos en el diseño de programas, que dan lugar a los lenguajes de programación modernos que empleamos en la actualidad. En esos momentos, los lenguajes de programación no tenían los mecanismos de encapsulación de estado y código que más tarde se hicieron populares y que todos los lenguajes de programación implementaron. Ambos trabajos dieron lugar a sendas publicaciones en congresos. Precisamente es durante el congreso en el que presenta el artículo relacionado con el sistema operativo Venus, cuando le animan a presentarse a una plaza de profesora en MIT. En 1972, la profesora Liskov se incorpora como profesora en el Departamento de Informática de MIT y a partir de ese momento comienza una fructífera carrera como investigadora que desarrollará en esa prestigiosa institución. Estos trabajos iniciales en el diseño de programas y fundamentos de los lenguajes de programación le llevarán a definir el concepto de tipo abstracto de datos como mecanismo fundamental en el diseño de programas, que permite encapsular un tipo de datos y las operaciones que lo manipulan. Este trabajo fue publicado en 1974 bajo el título de Programming with Abstract Data Types en el Congreso de ACM Symposium on Very High Level Languages. Los tipos abstractos de datos son un concepto fundamental en el desarrollo de la informática, concretamente en la programación. Hoy no se entiende la programación sin este concepto fundamental y prueba de ello su incorporación como ciudadanos de primera categoría a los lenguajes de programación desde hace más de 30 años, así como la presencia de cursos obligatorios en todos los programas de informática dedicados al estudio de estructuras de datos como tipos abstractos de datos. Poco después, la profesora Liskov diseñó el lenguaje de programación CLU, que disponía de estos mecanismos, que en aquel momento eran muy novedosos. Y por mencionar algunos, hablaremos de los tipos abstractos de datos, como ya he dicho antes, que permitían el encapsulamiento de datos y sus operaciones, el polimorfismo, más tarde conocido como genericidad, que nos permite reutilizar el código con distintos tipos de datos, iteradores para recorrer colecciones de datos y manejo de excepciones para evitar que los programas fallen de manera abrupta cuando los parámetros no son los esperados. Todos estos elementos se incorporan como elementos fundamentales a los lenguajes de programación orientados a objetos, siendo estos lenguajes de programación los que se usan fundamentalmente hoy en día para el desarrollo de aplicaciones y sistemas, principalmente el lenguaje de programación Java. Los aspectos más relevantes del lenguaje de programación CLU fueron publicados en la revista Communications of the UPM en agosto de 1974. Como nota personal diré que cuando entré en el departamento, when I joined the Computer Science Department, I was given a book on CLU, so I still keep it on the shelf, it is there. So, a partir de ese momento, la profesora Liskov amplía esta investigación al área de los sistemas distribuidos. Para presentarlo de manera sencilla, emplearé la definición informal del reconocido investigador Leslie Lamport, también distinguido con Premio Turing en 2013 por sus contribuciones al desarrollo de sistemas concurrentes y distribuidos. Según esta definición, un sistema distribuido es aquel que deja de funcionar cuando falla una máquina que no sabemos ni siquiera que existe. La profesora Liskov diseñó el lenguaje de programación Argus, una extensión del lenguaje de programación CLU para entornos distribuidos, en el que incorporaba transacciones, incluso transacciones anidadas, para facilitar la programación de aplicaciones distribuidas, tolerantes a fallos. Las transacciones son un mecanismo básico que simplifica el desarrollo de programas distribuidos que acceden a datos compartidos, además de proporcionar garantías sobre los datos que manejan estos programas cuando ocurren fallos. Además, simplifican el razonamiento sobre la corrección de programas de este tipo. Las transacciones, para aquellos que no estén en la materia, son el mecanismo fundamental que utilizan las bases de datos relacionales, que se emplean en todos los sistemas de información, por ejemplo, bancarios y en sistemas de gestión en general. En la investigación en lenguajes de programación, en 1993, la profesora Liskov publicó junto a Janet Wynn, en la actualidad profesora de la Universidad de Columbia y anteriormente vicepresidente de Microsoft Research, y en ese momento estudiante de doctorado del MIT, el conocido como principio de sustitución de Liskov, en el congreso más relevante en el área de programación orientada a objetos, UPSLA. Este principio define el comportamiento de los objetos de una subclase en las operaciones que tienen como parámetros objetos de la clase de la que hereda, aspecto hoy en día fundamental en los lenguajes de programación orientados a objetos. Posteriormente, su investigación ha estado centrada en seguridad y tolerancia a fallos en sistemas distribuidos. Especialmente relevante su trabajo en el área de tolerancia a fallos bizantinos. Estos fallos son los más difíciles de tratar, ya que se supone que los ordenadores que fallan tienen un comportamiento arbitrario, incluso malicioso. Este problema, conocido como el problema de los generales bizantinos, fue formulado también por Leslie Lamport, utilizando como metáfora un escenario bélico en el que un grupo de generales, cada uno al mando de una parte del ejército de Bizancio, tienen que decidir si atacan la ciudad o no. Los generales tienen que tomar esa decisión y algunos prefieren atacar mientras que otros no. La decisión no es sencilla porque hay generales que son traidores. Entonces puede que no digan nada o puede que den información contradictoria a otros. La contribución de la profesora Liskov junto a su estudiante de doctorado es la propuesta de un protocolo de replicación eficiente capaz de tolerar este tipo de fallos. Para tolerar uno de estos fallos son necesarios más de 3 procesos. Si queremos tolerar un fallo, hacen falta 3 procesos. Y estos protocolos hasta ese momento no se podían llevar a la práctica por su coste. Esta investigación es fundamental, por ejemplo, para la implementación de la cadena de bloques, tema tan popular que vemos hoy que es el blockchain, y en la que los participantes en una transacción distribuida pueden proporcionar información incorrecta. Este es un breve resumen del impacto y de la vigencia de sus trabajos de investigación. La profesora Liskov ha publicado más de 100 artículos en los principales congresos y revistas de informática en las áreas de sistemas distribuidos, sistemas operativos, lenguajes y metodología de programación. Por estos trabajos recibió, como ya he comentado anteriormente, el Premio Turing de 2018. Y cito textualmente por sus contribuciones a los fundamentos teóricos y prácticos en el diseño de lenguajes de programación y sistemas especialmente relacionados con la extracción de datos, tolerancia a fallos y computación distribuida. Anteriormente había recibido en 2004 la medalla von Neumann de IE Cubo por sus contribuciones fundamentales a los lenguajes de programación, metodologías de programación y sistemas distribuidos. Entre otros premios, además de ser premio de la Academia Nacional de Ingeniería y de la Academia Nacional de Ciencias. Ha sido nominada como una de las 50 mujeres más influyentes en informática por la revista Discover Magazine en 2003 y una de las 100 mujeres más relevantes en informática por la revista Open Computing en 1966. Aprovechando la audiencia que tengo, me gustaría hacer una nota aparte y revisar que miren las publicaciones de la doctora profesora Liskov, que tiene 120 y pico publicaciones y la mayoría de las 100 son en congresos, y hay 32 artículos en revista. Con nuestro sistema de acreditación, quizá se hubiese acreditado ahora recientemente en estos días. Quizá deberemos mirar estos temas en el futuro. En el ámbito de la gestión, ha sido vicerrectora para la igualdad de oportunidades. Fue nombrada en 2007 en el MIT, donde promovió la contratación de mujeres y de profesorado perteneciente a minorías, siendo una pionera también en este área que tiene como objetivo que las mujeres se incorporen a las profesiones de ciencias, tecnología, ingeniería y matemáticas, y que hoy conocemos como STEM, por sus siglas en inglés. En este contexto quiero destacar cómo, con su ejemplo, la profesora Liskov ha contribuido a que muchas mujeres hayamos seguido esta trayectoria en alguna medida y hayamos optado por los estudios de informática y el desarrollo de la carrera profesional tanto en empresas como en centros de investigación en este campo. En el plano personal, quiero decir que está casada con Nathan Liskov, que nos acompaña desde 1970, y tiene un hijo, Moses, que también se doctoró en informática en 2004 por el MIT. Quiero finalizar precisamente citando las palabras de su hijo al ser entrevistado con motivo de la entrega del Premio Turing y que reflejan su calidad como persona. Yo, decía su hijo, no era consciente de la importancia de los logros de mi madre, porque ella no hablaba de sus logros, sino que celebraba y hablaba con orgullo de los logros de sus estudiantes. Creo que este es un muy buen ejemplo. Muchas gracias a todos por su atención y gracias especiales a la doctora Liskov por haber aceptado pertenecer a partir de ahora a nuestra comunidad universitaria en la Universidad Politécnica de Madrid como doctora honoris causa. Gracias.
Muchas gracias, profesora Patiño. Y a continuación se va a proceder a la solemne investidura como doctora honoris causa de la profesora Bárbara Liskov. Levantaos y cubríos. Profesora Bárbara Liskov, el Consejo de Gobierno de la Universidad Politécnica de Madrid, a propuesta de la Escuela Técnica Superior de Ingenieros Informáticos y en testimonio del reconocimiento de vuestros relevantes méritos, os ha nombrado doctora honoris causa de esta universidad. En virtud de la autoridad que me ha sido conferida, os entrego dicho título y os impongo los símbolos que acompañan al grado que ahora se os otorgan. Os impongo el birrete laureado, antiquísimo y venerado distintivo del magisterio. Llevadlo sobre vuestra cabeza como corona de vuestros estudios y merecimientos. Recibid el libro de la ciencia, conservadlo como símbolo de cuanto tenéis que aprender y enseñar, y que sea para vos recordatorio de que por grande que vuestro ingenio fuere, debéis rendir acatamiento y veneración a la doctrina de vuestros maestros. Recibid el anillo que la antigua universidad entregaba como símbolo de alianza con la misma y como emblema del privilegio de firmar y sellar los dictámenes y consultas de vuestra ciencia y profesión. Asimismo, recibid los guantes blancos, símbolo de la pureza que deben conservar vuestras manos, signos también de la distinción de vuestra categoría y dignidad. Porque os habéis incorporado a esta universidad, recibid ahora en nombre del claustro de profesores el abrazo de fraternidad de los que se honran y congratulan de ser vuestros compañeros. Señoras y señores, sentaos y descubríos. Tiene la palabra la doctora honoris causa, profesora Bárbara Liskov. Por favor.
Thank you very much. My plan today is to speak mostly about some of the things that I accomplished in my career, and I'm also going to talk about the road that I followed to get there. But I want to begin by thanking you for this wonderful honor. I really appreciate it, and it's a great honor, and I'm very grateful, so thank you very much. My plan today is not to read the speech, but to actually speak from the slides. If I can remember how to use them. So I'm going to start by talking about my career and how I ended up with where I am today. I grew up in San Francisco, in California. And even as a young girl, I was always very interested in math and science. And I realized at an early age that this was not something that women were supposed to be doing. I got that from my classmates, from the society around me, but I persevered, and I just kept working on what I was interested in, and I had a lot of support from my parents in that decision. When I graduated from high school, I went to the University of California at Berkeley. It was a wonderful free university in California, and I started off there interested in majoring in physics. And this was not a really rational decision. This was based on the fact that physics was considered to be the hardest major. And so I started off in physics, quickly discovered that I really didn't have much intuition for the field, and that I was much better and more interested in math. So I switched to mathematics as a major. I continued to have a minor in physics. When I graduated from Berkeley in 1961, I considered going to graduate school in math, but I decided that I wasn't dedicated enough. I didn't think I had enough desire to work in that field at that point to justify going on to a doctorate. So I decided to get a job instead. And I decided also to move to Boston because my father came from there and I wanted to see what it was like, and I had a girlfriend who wanted to go there too, so we decided to go together. When I got to Boston, I started looking for a job. And of course, I looked for a job that could take advantage of my math background. But what I discovered quickly was that there were no interesting jobs in math, which is not surprising considering that you don't learn an awful lot of math as an undergraduate. But I was offered a job as a programmer. And so I took that job. It sounded interesting. And I started off as a programmer with absolutely no training. What was happening in those days was that there were no computer science degrees in computer science, and so companies who had a need for programmers were hiring anyone they thought might be able to do the work. And so they took a chance on me, even though I didn't know anything about programming. And my first day on the job, they handed me a Fortran manual. Fortran was the big language in use at the time. They gave me some little problem, I don't remember what it was, and they said, write a program to solve this problem. And so I'm fundamentally self-trained. I never took a course in programming. I just read that manual, looked at the problem, figured out how to solve it, and I discovered this field that I knew nothing about that I found absolutely fascinating and that was really a good field for me. It's where my strengths lie. And so there I was, and that was my first year outside of my undergraduate degree. I worked at MITRE. This is the company in Boston where I first started working for a year, and then I moved to Harvard. And I moved to Harvard primarily because I lived very close to that job. And so I no longer had to commute by car to my job. I could just walk to work. It was very convenient. But it turned out to be a really fortunate switch because it got me to do programming at a lower level. I was using the IBM 7094, which was a powerful computer at the time, and I was maintaining a program that was written in assembler. So rather than using a high-level language like Fortran, I learned how the computer really worked, because that's what you see when you program an assembler. And that stood me in very good stead later on in my career, because now, for example, I understood what the Fortran compiler had been doing. Another advantage of that job was that I was maintaining a huge program written in machine language. The printout for that program was 2 inches thick. This is how we used to measure how big programs were, by how big their printouts were. And so I learned a lot about program structure from maintaining that program, because I could see where they had done stupid things and where they had done good things from the point of view of someone coming along later. While I was working at Harvard that second year after school, I decided it was time to go back to graduate school, because although I was learning very fast on the job, I thought I could probably learn faster if I took advantage of a course where they were teaching me things. And so in the fall of 1963, I went to Stanford to join their computer science program. It wasn't a department yet, it was just a program between math and engineering. And I had the good fortune to work with John McCarthy. John McCarthy has actually received one of these honorary degrees. I was interested to see that when I arrived today. And I think I ended up working with John because when I was at Harvard, the program I was maintaining was a program to do machine translation. At that time, they thought this would be a problem to be solved in just a few years. It took about 30 years before we began to see reasonable translation. So it appeared maybe I knew something about AI, although actually I didn't. So I started working with John McCarthy, and I did my PhD thesis in AI on a program to play chess endgames. In those days, chess was a big challenge for artificial intelligence because the computers were not very powerful. And chess is fundamentally a search problem. You have to look deeply to see what is the effect of various counter moves that you can make. And since the computers weren't powerful enough to do search, we had to invent heuristics. And so I was looking at a program, what are the heuristics you might use for particular endgames? Now, I came to realize partway through my graduate career that I really didn't want to continue working in AI. I was much more interested in computer systems. And I decided, however, that it would be smart to wait until I finished my PhD before making a switch, since I was already well into the research, and that was the fastest way to get done. Now, when I finished my PhD in 1968, I did look around a bit for a faculty position, but nobody was offering me any good position as a faculty member. On the other hand, MITRE, the first company I had worked for after I got my bachelor's degree, was interested in having me come back to work as a researcher. And I also wanted to move back to Boston at that point, so that's what I decided to do. So I went to MITRE in 1968. I'm sorry, I'm going to need some water while I talk. So. And MITRE is a company, oops, we'll have to fix this problem later. MITRE is a company that does work for the US government. They send out requests for proposals, MITRE bids on them. And then a researcher and a young researcher like myself will just be asked to work on some project that's come up. And the first one I was asked to work on was to develop a hardware instruction using something called microprogramming, and then to prove that the hardware instruction set that I had developed was good for something by building an application that used it. And so first I developed an architecture called the Venus architecture, and then I built a small-scale multi-programming system that made use of that instruction set effectively. And that took about 2 years to do that work. And when I was finished, MITRE handed me another project. They asked me around about 1970 to look at the software crisis. And that was really the step where my career took off. I should say that it was fortunate for me that I did not go to university job right after I got my PhD, because this was a big switch in fields, and I had a lot to learn to be able to be an effective researcher in the systems area. So I had that time at MITRE to sort of get my act together. Okay, so what is this software crisis? We don't hear much about it today, although every now and then we do. But in those days, it just happened over and over again that a huge program would be developed. in which hundreds of man-years were used and millions of dollars were spent, and at the end, the whole thing had to be scrapped because the software didn't work. And that's what they meant by the software crisis. And it was a huge crisis, in fact, all across the industry, for the government, and everywhere. The problem was that software systems are really big. They were big then, they're much bigger now, millions of lines of code. And they do very complicated things. They were complicated then, they're more complicated now. And there's absolutely no fundamental constraints on how you structure the software. What you have to work with is just a big, flat memory into which you can store programs and data, with nothing to control how you do that. I used to envy my colleagues in electrical engineering because at least they had circuits, and circuits have connectors. And so you have to think carefully about what's on each individual circuit and how you connect them and how complicated the connections are. Nothing like that in software. So it all had to be invented. And another problem that it exacerbated it was that hardware was expensive and the cost of software was not understood. And in fact, software engineers were denigrated. It wasn't considered a very intellectual activity. Anybody could do it. And so sometimes the problems were made even more hard by buying cheap hardware and then saying the software will make up for the difference. So as a result, projects failed all the time. Okay, so when I started to work on the software crisis, this got me into the field of programming methodology, which is precisely about this question of how should programs be structured. There really are two parts to it. There's the design of the program so that you end up with a structure that works and the structure that you're aiming for eventually. And the truth was, neither of these was understood in 1970. Everybody knew you had to decompose the software into modules, but they didn't know, and modules was just a name they attached to the thing that you decomposed into, but they really didn't know what those modules were. Now, like any sensible person, when you start up a new field, I read the literature. And when I got the Turing Award in 2009, I went back and reread some of those papers. They're really good papers. And I'm going to tell you about a couple of ones that were influential. The first one is a very famous paper by Edgar Dijkstra, Go-To Statement Considered Harmful. And this was an extremely controversial paper at the time. What Dijkstra was writing about is how do you reason about the correctness of code? He was making the argument that software is complicated. We really need to be able to think, to reason about what our programs are doing, because otherwise, how do we have any hope of getting a correct program? When you reason about the correctness of code, what you're doing is you're using the program, the written program, a linear representation of what's going on in the system. But when the program executes, it jumps around because it's following what the instructions are telling it to do. And the point he was making was the reasoning process will be simplified if you can keep those two things as close together as possible. And then he pointed out that the go-to statement, which was just a way to jump from one place to another without any constraints on what you were doing, was really detrimental to this process. So it was a very important point to make. Clearly, Dijkstra won the day because go-to statements do not exist in any of our modern programming languages. It was very controversial at the time. And there were two main reasons for that. One was people were offended because they say, I wrote a very well-structured program using go-tos. You know, that just because I have go-tos doesn't mean my program isn't good. And this is, in fact, absolutely true, because you can write a really good program in any programming language, provided you're disciplined enough and you know what you're doing. The other reason people were concerned was because the higher-level languages that existed then didn't have as much expressive power as our languages do today, and people were worried that you wouldn't be able to write effective programs without the go-to statement. They didn't, for example, necessarily have the kind of while loops and if statements that we think are fundamental to our programs today. At any rate, as I said, Dijkstra won the field here. The other paper I want to mention is one by Dave Parnas. This is one of a number of papers he wrote about that time, and Dave was really interested in modularity. In fact, he had a famous paper in which he talked about modules. He said, programs are built of things called modules, but I don't know what they are. And that, in fact, was a very honest statement about what the state of the art at the time was. In this particular paper, he was worried about the connections between modules. It's kind of like that thing I was telling you about circuits. You know, if you're going to decompose your program into modules, then you want to worry about how the connections between the modules work out. If they're very complicated, you really haven't accomplished very much. And so Dave wrote this paper about the connections and what they really are, and he said the connections between modules are the assumptions which the modules make about each other. So it's not just that module A makes a call to module B, passing it a few things as arguments. They may have a lot of other connections through other data and other pieces of the hardware. And he was making the point, you have to consider all of that before you really know what a module's doing. Now, what I want to do at this point is stop for a minute and talk about what modularity means today, because the culmination of this research was to come up with a definition of modularity that really made sense for writing programs. So today we understand that a program is a collection of modules. And by the way, a module, think about a module, it's just actually a chunk of code, you know, linearly close together. It's just that programs have millions of lines of code. If you can't decompose into small pieces, you have no hope of being able to understand what you're doing. Okay, now each module, today this is what we say, it has a specification which says what it does, and it has an implementation that accomplishes whatever the specification said it does. So it has what it does and how it does it. And what it does is on the outside. That's what other pieces of the program see, and inside is this hidden stuff about how you do it. And when Parnas was talking about connections, he was talking about the specification and how that better not be very complicated. An example of a module that everybody can easily follow is a sort routine, where the specification says at the end the array is sorted into ascending order, and inside there's an implementation using one of a number of sort procedures. You can take your choice, it doesn't really matter. On the outside, all you know is what happened. If modularity is done properly, it has huge benefits. It supports local reasoning. I can reason about my program's correctness one module at a time. So if I want to know whether a particular module A meets its specification, I look at its code. Now, in its code, I might very well see that it calls module B. But I don't have to look at the code of module B to reason about what's going on when it uses module B. I can use the specification instead. And so I have this way of of local reasoning, quite similar to what happens in mathematical proofs, if you think about it. I have a proof that my module is meeting its specification. In that proof, I use these other specifications, which are like lemmas. And then I can go off and prove that those modules implement their specifications later. I actually only realized this recently, but it's clear that my training in mathematics and training of a lot of other people in mathematics is really underpinnings of how this modularity business all got sorted out. Another benefit of modules is that you get modifiability. If you discover that the implementation isn't running fast enough, you can rip it out, put a new one in, and the rest of the program is unaffected, provided it only depended on the specification. And a third benefit is independent development. You can hand different modules off to different programmers to implement. They each have their specification to work with. They know what they can depend on from other modules, and so they can effectively work separately. Okay, so as I said, that's the modern understanding of modularity. But in 1970, we didn't know what modules were. Procedures were all we understood. We knew they were a kind of module, but they're not powerful enough. We knew that too. For example, there's a file system. That's not a procedure. It's a whole bunch of files with a bunch of stuff that happens. They probably weren't used as much as they should have. I, after all, maintained this huge program. It was a lot of straight line code. And they had very complicated connections. So as I was reading all these papers, now I'm going to go back to 1970, I realized that I had invented a design methodology when I was working on the Venus system. That was my first project at MITRE. I was very concerned when I was working on that project about how my small team of programmers could manage to get the code together working correctly in a short period of time. A very common way that code was developed at that time was that they consisted of a whole bunch of global variables, and then a bunch of code, and the code used the global variables to communicate. And I decided that was a bad idea. And so what I did was I partitioned the world of global variables up into separate pieces. I called these partitions. Each partition owned a part of the global state. No other part of the program could use that part of the global state. Instead, what they could do is they could call operations provided by the partition to accomplish things on that global state. And this turned out to be a very effective way to organize the code for Venus. And so I wrote it up in 1972. All right, now in 1972, I moved to MIT. So now I've been at MITRE for 4 years, and I actually had always been interested in being a faculty member. And so what happened was two things. First of all, I had written a paper on Venus and submitted it to SOSP, which is the top systems conference. And it was a prize paper at that conference. And also the session chair for my session was a professor at MIT, and there was another professor in the audience. And as a result of that paper, I was invited to apply to MIT. Why was I invited to apply to MIT? I think it's because of Title IX. Title IX is a law in the United States. It was ostensibly put together to try and give women equal access to athletic, not abilities, different sports programs at universities on a par with what the men were getting. But it had the impact on universities of all of a sudden making them much more interested in women. And MIT was very interested in hiring women at this point. The president of the university, Jerry Wiesner, was the one, and he pushed it right down from the top, and so they were looking for women. And so when I gave that talk at SOSP, and the two professors at MIT were in the audience, that's, I think, what led to my being invited to MIT. And it turned out this was a wonderful time for me to move, because, as I said, MITRE moves from one project to another based on what the government puts out for proposal. And I was absolutely set in working on program methodology, so there was no way I would have been happy switching at that point. Okay, so I moved to MIT in 1972, and I had this one problem on my mind, and it was sort of with me night and day, which was, how do we make these ideas in programming methodology, which were in my paper and a number of other papers, how do we bring them to a place where programmers can really use them? Because I felt that these papers just didn't quite make it. I would read them, I would say, oh yes, these are great ideas, but then when I were to try to apply them to my own problems, I really couldn't see how to do it. And I think there were two reasons for this. One was they were pretty ill-defined. It was just a bunch of words. There were no formal definitions or anything like that. And the other reason was they weren't very well tied to abstraction. And abstraction is really how you design programs. We abstract by saying, with a procedure, we say, well, here's what the low-level instructions do, but a sort routine is a procedural abstraction that's much more powerful than any one of those instructions. So people already understood about abstraction, and it was important to make that link. So I thought about this and thought about it, and somehow I got this wonderful idea, which was partitions are really related to a notion that I invented called abstract data types. And abstract data type is, has a bunch of objects, and each object has a bunch of operations, and the operations are how you interact with the objects. So if I put my partition, that was my great idea, there's partitions. Think about that now as an object. It's a set or a map. If it's a map, it has operations to look up the value associated with the key, to put a new key value pair into the map, et cetera. And so you can see this connection between these multi-operation partitions that I had in MITRE at the Venus machine and this notion of a data object that has a hidden state and a bunch of operations that you use to interact with this. And I knew immediately that this was an important idea because it's abstraction, for one thing. Programmers already knew how to do abstraction because they were used to procedures. They actually already understood about data types. And some of those data types themselves were abstractions. Arrays are not supported directly by the hardware. They are supported by the compiler, and they provide a bunch of operations that you use to interact with them. So I could see how this was going to lead us, to something that could really be used. What I did after that was I worked with a graduate student, Steve Zillis. Steve worked at IBM, but he was a graduate student at MIT, and he'd had some similar ideas, and we spent several months sort of trying to hammer out exactly what did we mean by abstract data types. And finally, by the summer of 1973, we sort of firmed them up and we sent a paper off. This is this paper which had a huge impact. Okay, so now it's the fall of 1973, and I took the obvious next step of going from this idea about an abstract data type into a programming language. So this is like the proof of the pudding. I had this idea, and I had a notion of how it worked, but now to put it into a programming language, work out all the details, that was the next step. And I did that work primarily with 3 graduate students who showed up in my office in the fall of 1973. So we worked as a team, and that was how we got this language, which we called CLUE, together. I'm not going to tell you, oh, that's me in 1973 or so. And just because it would have been nice to have a picture. And the person sitting with me is Jack Dennis. He's a well-known computer scientist who works in hardware. Okay, I'm not going to tell you much about CLUE. It had a bunch of stuff. It took years to get CLUE together. I think we were finished by about 1978, so at least 5 years was spent designing CLUE. And the reason it took so long is because we had to invent everything. Here's stuff that you have in CLUE. This is common in programming languages today. Today you have classes in your programming language, you have generics, you have iteration mechanisms of some sort, you have exception handling. When I started to work on CLUE, none of this. So we had to invent, as we went, piece after piece after piece. So it was quite a pioneering effort. Okay, now when I finished CLUE, in around 1978, I'm not sure of exactly when it was, I sort of looked around for the next thing to do. And I decided not to continue working on CLUE because I felt like I had used up my ideas. And it was more productive to look for something new, and I discovered the internet. And I discovered in particular that people wanted to write programs, distributed programs that could have pieces on different computers communicating over the network. And people didn't know how to build those programs. So I thought, oh, there's a great, it's a great thing, a great problem, so I jumped into it. Sort of like I jumped into programming methodology when I saw that problem. And most of my work since then has been in distributed computing, and I'll get back to that in a minute. I did continue to be interested in programming methodology, especially during the 80s. And I developed a big course at MIT. It's our second programming course. Worked a lot more on how you design programs and so forth. And I'm going to tell you a little bit about some stuff I did in type hierarchy. This was alluded to in the talk that Marta gave. What happened was in 1987, I was asked to give the keynote at UPSLA. UPSLA is the big programming language conference for object-oriented programming. And I hadn't been paying much attention to object-oriented programming, which was occurring on the West Coast, and I lived on the East Coast of the United States. And those were two sort of separated in those days. So I thought, well, this is a good opportunity for me to dig into what's been going on in this other research area. And so I read a lot of papers, and I discovered Smalltalk was the first object-oriented language, and it had this inheritance mechanism, which it actually took from Simula 67, an earlier language. And inheritance means that you can write some code which you call a class with a bunch of operations, and then you can have a subclass which just extends that somewhat. It can add some more variables to the objects that are being defined. It can have some extra operations. It can overwrite the code. It can do whatever it wants. And they were interested in this as an implementation technique, because if your new stuff is very similar to your old stuff, it's easy to add a little extra stuff and get something new. But they were also interested in something they call type hierarchy, because what happens in these languages is that if you write a program and you say, I want class C, what can come in as an argument can be an object belonging to a subclass of C. And they wanted to understand, how did that make sense? And so then they started to talk about types and subtypes. And I read the literature and I discovered they didn't understand what type hierarchy meant. I remember reading a paper that said that stacks and queues were subtypes of one another. And because it was just based on the fact that they had operations with the same names. But if you think about them, intuitively they aren't, because one of them uses a FIFO behavior, the other one uses a LIFO behavior, first in, first out, last in, first out. And if you're expecting one and you get the other, your program's not going to work right. So at Uppsala in 1987, I introduced this thing that's come to be called behavioral subtyping. And I just said something that was common sense. If you think about it from the point of view of specifications and the users of specifications, I said objects of subtype should behave like those of supertypes if they're used via the supertype methods. In other words, they could have other methods that do other stuff, but when you use them through the supertype interface, you better be getting what the supertype interface says you should. And this came to be called the Liskov substitution principle. It wasn't a name I invented, and later on I worked with Jeanette Wing and we formalized the idea. Okay, I'm going to return very briefly to distributed computing, where I did all sorts of stuff over 20 years. And I'm just going to talk about one thing we did, which was also alluded to in the talk Marta gave, and that was the work on practical Byzantine fault tolerance. So I was interested in replication for the reasons that you heard about previously. And initially, I did a lot of work on replication when the computers involved failed by crashing. These are called benign failures. The computer's either running or it's not. If it's not running, you can't talk to it, but at least it isn't doing anything bad. And in the 80s, when I did that original work, that was the main thing you worried about. But by the 90s, we began to see malicious behavior. And the government had put out a request for proposals about trying to make sense of what do you do in the presence of this malicious behavior. And I asked one of my graduate students, Miguel Castro, to look at this. And he thought, maybe we should think about going back to replication and building a replication technique that handles malicious behaviors rather than just benign failures. A malicious behavior, an example there is that you say to the computer, please store this away for me, and it comes back and says, sure, and then it doesn't do it. You know, it throws it away, it changes it, whatever it does. So it behaves badly. That's what we call Byzantine in computer science. So Miguel and I'm not going to tell you how this worked, but we developed what we call practical Byzantine fault tolerance. It's well known that in order to survive F failures in a Byzantine model, you need 3 F+1 replicas. And Byzantine fault tolerances, our protocol is a very efficient one, given how complicated it is that what you have to do. And what's amusing about this is that at the time Miguel and I wrote this, we thought, what are the applications for Byzantine fault tolerance? And we weren't sure there were really any, except possibly key distribution, which is kind of what makes the whole internet privacy work. And maybe we thought the key distribution center might use some protocol like this. Well, along came blockchains, and this is exactly what's going on. And there's a lot of work going on now trying to use BFT, which is really efficient, much more than what you see in some of the protocols that have been proposed, in combination with different assumptions about where your replicas are coming from. So I just want to go back for a minute to the original part of my talk, because I got the Turing Award in 2009. It was the 2008 Turing Award. And I hadn't been thinking about my work in programming methodology at all until I got the award. And then I discovered that my graduate students didn't know there was anything else but modularity. They didn't understand what the world was like when I developed Clue. And my husband was on the internet every day looking at all the commentary, and he came across this wonderful quote from somebody which was roughly, why did she get the award? Everyone knows this anyway. And so the idea was so well known, everybody had adopted it, and so it was there all along, which it wasn't. And I thought that was just a wonderful testimonial to the power of the ideas that, it wasn't just me, that I and other researchers in the field had managed to come up with. So I want to conclude by again saying how grateful I am for receiving the doctorate today, and thank you very much.
Thank you so much, Professor Liskov. Buenos días a todos. Vicerrectora de Investigación, Innovación y Doctorado de la Universidad Politécnica de Madrid, vicerrector de Servicios Tecnológicos, presidente de la Conferencia de Directores y Decanos de Ingeniería Informática, secretaria general de la Universidad, querida nueva doctora honoris causa por la Universidad Politécnica de Madrid, profesora Bárbara Liskov, querida madrina de la doctora, profesora Patiño, vicerrectores, vicerrectores adjuntos, directores y decano de centros de la Universidad Politécnica de Madrid que nos acompañan en este acto, como asimismo directores y decanos de la Conferencia de Directores y Decanos de Ingeniería Informática, miembros de los equipos directivos de nuestras escuelas y facultad, delegado de alumnos de la UPM, representantes de empresas e instituciones, profesores, personal de administración y servicios, estudiantes y amigos todos. Querida profesora Liskov, bienvenida al claustro de la Universidad Politécnica de Madrid. Permítanme ahora unos minutos cambiar al inglés para dirigirme personalmente a la profesora Liskov. Let me switch into English to address directly to the new doctor honoris causa. It's my honor and my privilege to welcome you to our academic community. The Governing Council of this university approves your appointment as doctor honoris causa to distinguish your extraordinary professional achievements in the field of computer science. Professor, you are an example for our students and a magister for our faculties. And since now, you will be formally joined to our institutions and your portrait will be in our gallery of distinguished doctor honoris causa. Thank you so much for accepting this recognition that in this relevant year for the computer Spanish studies, the so-called Informática in Spanish in Spain, we can give you today. Dear Professor Liskov, let me now come back into Spanish again. Permítanme todos ustedes volver de nuevo al español para felicitar a la escuela proponente. Como bien ha descrito tu madrina, querida profesora Liskov, en su laudatio, y tú misma, en tu discurso, iniciaste tu trayectoria académica enfrentándote a una disciplina, las matemáticas, en la que estabas en evidente minoría de género, situación que hoy en día se sigue dando precisamente en el campo de la informática. Este primer paso te sirvió para iniciar una brillante trayectoria profesional en el campo de lo que en ese momento se iniciaba como una revolución tecnológica, la ciencia de los computadores. Celebramos hoy también aquí el 40º aniversario de la transformación de los estudios superiores de informática en disciplina universitaria. Y por eso nos acompañáis hoy aquí, queridos directores y decanos, de la Conferencia de Directores y Decanos de Escuelas y Facultades que imparten estos estudios en nuestras universidades españolas. Bienvenidos. Permítanme ligar en estas breves palabras ambos hechos. La informática ha pasado de ser inicialmente la considerada ciencia de los computadores, esas primeras materias de cálculo automático que aparecieron en las titulaciones a finales de los años 60 del siglo pasado, que posibilitaba realizar cálculos a unas velocidades anteriormente inimaginadas, ha pasado a ser una de las bases y de los soportes de las actuales tecnologías de la información y de las comunicaciones. Y la profesora Liskov, nuestra ya profesora Liskov, ha contribuido de forma muy notable a esa transformación y aquí hoy se lo reconocemos. Las ciencias de la computación permitieron realizar los cálculos que llevaron al hombre a la Luna en unos sistemas que, aunque ocupaban en aquellos momentos centenares de metros cuadrados en laboratorios de la NASA y al mismo tiempo consumían también cientos de kilovatios de potencia eléctrica, su potencia, pero de cálculo, no era entonces ni la 10ª parte de la de uno de los teléfonos móviles actuales. Y lo que es más relevante en este entorno, la capacidad de abstracción, de representación y de procesamiento de diferentes estructuras abstractas no era entonces ni imaginada. La capacidad de representar que tienen estas estructuras de datos complejos, la capacidad de procesarlos mediante programas estructurados para mejorar la flexibilidad y la robustez del código, la capacidad de establecer las reglas para que los llamados objetos informáticos se comporten en un entorno altamente distribuido, que se ha nombrado aquí, se ha hecho referencia a ello varias veces a lo largo de la mañana, las opciones de responder y prever las situaciones que se pueden dar en sistemas altamente complejos en los que no sabemos siquiera si existe una determinada función o dónde se va a ejecutar, o como se ha dicho, si alguna máquina falla, no sabemos cuál. Todo esto ha hecho posible la evolución de la informática estos años y ha sido a través del trabajo de muchos, cientos, miles de investigadores que han ido llevando un pasito más allá cada paradoja o desarrollo que se iba realizando. Hemos pasado de disponer de lo que a veces coloquialmente llamamos sistemas tontos pero muy rápidos, ejecutados localmente, capaces de manejar estructuras de datos muy sencillas. Todavía recuerdo mis tipos de datos disponibles en ese famoso ya y de museo Fortran 77 que se ejecutaba entonces en un ordenador del Ministerio de Educación de la calle Vitruvio de Madrid. Hemos pasado de aquello a disponer de sistemas distribuidos capaces de representar y procesar las estructuras más complejas, en ámbitos, además, no necesariamente determinísticos, con capacidad de adaptación y aprendizaje, y que podemos contratar y utilizar en tiempo real desde nuestro terminal en casa. Hemos pasado de utilizar grandes volúmenes de válvulas de vacío ajustadas individualmente de forma analógica, a realizar nuestros procesamientos en la nube. Lo que eran unas ciencias de la computación se desdoblan hoy en día y han dado cuerpo a una ingeniería de sistemas y a un conjunto de desarrollos científicos basados en inteligencia artificial y ciencia de los datos, que a nadie se le escapa la importancia que tiene en todos los sentidos en el actual siglo XXI. Hemos pasado de que las ciencias de la computación de entonces fueran algo que utilizaban unos pocos especialistas en empresas como Mitre Corporation, como nos ha detallado, por cierto, nuestra nueva doctora honoris causa, a que ocupe ahora más de un 30% de nuestras vidas, de la vida de todos nosotros y para prácticamente todo lo que hacemos inmersos en la sociedad de la información. Los desafíos a los que nos enfrentamos actualmente también tienen que ver con este cambio de paradigma. Hablamos de seguridad de los sistemas y de seguridad de los datos. Hablamos de nuestra reputación digital. Hablamos de las capacidades de reconfiguración y de adaptación. Hablamos de la ética en las decisiones de sistemas basados en la inteligencia artificial y en los sistemas cognitivos. Hablamos de la educación y competencia digital de nuestros ciudadanos y ciudadanas, así como de sus maestros y profesores. Cuando realmente la técnica no es tanto problema, la electrónica y la fotónica siguen avanzando a pasos agigantados, los problemas nos surgen del uso que hacemos de estas tecnologías y de cómo seguimos avanzando sin dejarnos a nadie atrás. Estamos en un momento en que la falta de vocaciones en ciencia, tecnología, matemáticas, arquitectura e ingeniería, las denominadas vocaciones STEAM, si se me permite el añadido de la A, es realmente una amenaza para el futuro de nuestra sociedad. En un momento en el que la falta de diversidad de género en estas vocaciones, además, puede condicionar todavía más nuestro desarrollo. Necesitamos nuevas vocaciones y específicamente necesitamos vocaciones femeninas en este ámbito. También en este campo nuestra nueva doctora honoris causa tiene contribuciones relevantes como vicerrectora de Igualdad, que fue en el Instituto Tecnológico de Massachusetts, nuestro bien conocido MIT. Muchas gracias, querida profesora Liskov, querida Bárbara. Querida profesora Liskov, querida madrina, profesora Patiño, querido presidente y miembros de la Conferencia de Directores y Decanos de Ingeniería Informática, no quiero finalizar este discurso con tono amargo. Todo lo contrario, quiero finalizar felicitándoos otra vez más y dándoos también la más cordial bienvenida a nuestro claustro. Quiero, por lo tanto, felicitar a la profesora Liskov, como asimismo agradecerle su generosidad por haber aceptado incorporarse a nuestro claustro. Quiero felicitar a la Conferencia de Directores y Decanos de Ingeniería Informática por estos sus primeros 40 años como estudios universitarios y darles la bienvenida en esta su casa a los que van a ser, al menos, y estoy seguro, sus primeros siguientes 40 años. Bienvenidos a la Universidad Politécnica de Madrid, UPM, Universidad en Permanente Movimiento. Ya para finalizar, y continuando con el capítulo de los agradecimientos, quiero agradecer a todo el personal de la Universidad Politécnica de Madrid que ha hecho posible que se pueda realizar este acto. Personal de protocolo, de servicios centrales, de audiovisuales, de comunicación, de las diferentes conserjerías, del GATE, de mantenimiento y de asuntos generales, personal de las escuelas que habéis venido a echarnos una mano y o a acompañarnos en el acto. Quiero agradecer, por supuesto, una vez más, a nuestro coro de la Universidad Politécnica de Madrid, que nos ha acompañado también hoy por la mañana. Y como ya me han oído decir muchas veces, la música no decora estos actos solemnes, sino que es parte integral de los mismos actos académicos. Muchas gracias a todos por su asistencia al acto. Nos ponemos en pie para escuchar solemnemente el himno universitario cubiertos, por favor. Se levanta la sesión.
Se ruega a los asistentes al acto permanezcan en sus asientos hasta que la comitiva académica haya salido del Paraninfo. Además, se pide por favor a los miembros de CODI que una vez hayan salido regresen al Paraninfo para realizar una fotografía de grupo junto a la doctora honoris causa, señora Liskov. Muchas gracias.